right, so video number 2 of our equilibrium unit has to do with the equilibrium law in chemical reactions. And so we're going to look at how to write the equilibrium law if I give you a chemical reaction. So first off, in order to do this, I'm going to erase this because I'm going to explain it, is the equilibrium constant. The equilibrium constant is KEQ. Okay? So if I'm given a chemical reaction, A plus B equals C plus D, where my lowercase letters are the coefficients in the balanced chemical equations, then my value for KEQ looks like this. Okay, so it's always products divided by reactants, so you can see my C and D are at the top, okay, and my A and B are at the bottom. You need your concentrations of your reactants and products plugged in, and then you end up using your coefficients as exponents. So this value of KEQ, it's a constant, it's dimensionless, and its value changes with the temperature of the system. So that means if you have a certain reaction happening and it reaches equilibrium, if you change the temperature, the equilibrium has to sort of reestablish itself, and that means the concentrations change, which means your value for KEQ changes. What's good about it is that it is dimensionless, so you guys don't have to worry about units for KEQ, which is kind of nice. Equilibrium expressions are always written with the products as the numerator and the reactants as the denominator, just like I explained. The exponents in the expressions are the same as the coefficients in the balanced chemical equation. And what we do is we use this value to predict the amounts of reactants and products at equilibrium given the amounts of starting materials. So I'm going to show how that happens later on. So, oh shoot. I thought I had all of this erased. So, it says here, write the equilibrium law expression for the following reaction. So hopefully you didn't see that before I erased it. But pause the video and see if you can write out your expression for KEQ knowing it's going to be the concentration of your products over the concentration of your reactants, okay? So here's the reaction I want you to focus on. Can you write out the value for your equilibrium constant? So pause the video now because I'm going to take up the answer. All right, so if I'm looking at this, if I'm looking at my products, the only product I have is ammonia, so that's NH3. And I'm going to put that to the exponent 2 because of my coefficient. I'm going to divide that by my reactants. So in this case, I've got N2 to the exponent 1 because there's no coefficient in front of there. You don't necessarily have to write anything in there. I'm just doing that to clear things up for now. And my other reactant is H2, and that's going to be to the exponent 3. So there is my equilibrium law expression for this reaction. Simple as that. There are some rules. So the rules are, first we already kind of went through the first one. It always has to be products on the top and reactants on the bottom. And it says that solids never appear in equilibrium expressions, and liquids and solvents never appear in equilibrium expressions. Why is this? Basically, if you look at the second to last point, it says the concentration of a pure liquid or solid is unchangeable. In fact, we usually measure solids with mass, not with concentration. So therefore, they're constant and they're not put into the equilibrium expressions. So let's go through the first example. S plus O2 gives you SO2. If I were to write the equilibrium expression for that reaction, it would look like this. So again, I've done products divided by reactants, but I've eliminated my sulfur as a solid because there's no concentration for that. There's no value for concentration. So it ends up being your concentration of SO2 divided by your concentration for O2, and they're both to the exponent 1, which I didn't bother writing in, but you can if you want. For the second one, liquids and solvents never appear in the equilibrium expression. So for this one, I'm not going to bother writing in H2O because there's no concentration for water. So my expression would look like this. I've got my ammonia and my hydroxide ions on top. Those are my products. And I've got my reactants on bottom, but I didn't include water. All right. Again, my writing is still there. I thought I had erased all of these. So let's go through one step at a time here. What's wrong with these examples? So if I have the first example and I give you this equilibrium law, what is wrong with that? The second one, if I give this as your KEQ value, what is wrong with that? And the third one, what is wrong with that? So take a minute, pause. I'm going to go through the answers now. So the first one, mistake that I made was I wrote reactants over products. And I'm going through these because these are very common mistakes. So I used my concentration of my reactants on the top and my products on the bottom. So I should basically be flipping those two. For the second one, I have products over reactants, which is good, check. But I included a solid, which I should not have included. So that AgCl should not be in there. Everything else is good. And the last one, what's wrong with it? I'm sure you saw me erase this earlier, but basically there is nothing wrong with that one. I've got my products on the top, reactants at the bottom, and I used my coefficients here as my exponents, 1 and 1. All right. Oh, shoot. And again. Okay, ignore all my writing for a second while I erase it. So let's go through this example, and we're actually going to write out the equilibrium expression for this and do some calculations. So I've given you a chemical reaction. 2 NaCl gives you 2 NO and Cl2. If you place 2 moles of NaCl in a 1 liter flask, you seal it up, equilibrium, you find 0.66 moles of NO, which is one of your products. Calculate your value for K, so calculate your equilibrium constant. Remember I told you in the last notes that a table of concentrations or an ice chart is your new best friend? Here it is. So I've got my initial concentrations, my change, and my concentrations at equilibrium for each one of my reactants and products. Remember, I said up in the question, place 2 moles of that in a 1 liter flask. So if we go back to what you know from grade 11, concentration is moles divided by volume. So I have 2.00 moles in a 1 liter flask. So that's how I got 2 divided by 1 is 2. So that's how I got 2 moles per liter there. And if that's the only thing that I'm putting into my flask, then I have nothing as a product. So I'm going to seal it up, wait for the reaction to happen. As it happens, my concentration of my reactants is going to go down by 2x. Remember to use your exponents in here. My concentration of my products have nowhere to go but up. So this one's going to go up by 2x, and Cl2 is going to go up by x. Again, make sure you bring your coefficients down in there. Then it also said in the question that at equilibrium, I have 0.66 moles per liter of NO. That is equal to 2x, because I just said I'm going to go from 0 to 2x. When I add them up, that's 0.66. That means x equals 0.33. So this has now given me my concentration for Cl2, because my Cl2 is just x. So this is 0.33. And my final concentration for NaCl, my reactants, is going to be 2 minus 2x, or 2 minus 0.66, or 1.34. So now that I've got my ice chart with all of my concentrations, now I can actually calculate my value of K, which is what the question is asking me to do. So I'm going to do that on the next slide. So when I calculate K, I'm going to use, this is wrong, sorry. I'm going to use, oh, of course, now the whole thing erases. Using the equilibrium law. So remember from your last, from the last slide, or what's in your notes, that the equilibrium law, KEQ, is always products divided by reactants. So in this example, it's NO squared, because there's a 2 in front of it, times our concentration of Cl2, divided by your concentration of NOCl2 squared. Then all I have to do is, because I'm dealing with all these concentrations at equilibrium, I'm going to plug in the last row from my ice chart. I'm going to plug those numbers in. So I'm left with, my concentration of NO was 0.66. You can take that squared times 0.33 divided by 1.34 squared. When I do that, I get 0.08. That's a value for a KEQ. Remember that your value for KEQ has no units. It's dimensionless. Units. There we go. All right. If we look at the last point, it says the equilibrium constant for the forward reaction and reverse reactions are reciprocal values. So that means, I'm just going to erase this and write this up here, that if you have your value for K, if you want the reverse reaction, we call that K prime, and it's going to be 1 divided by that answer, okay? Or another way to write this equation, the exact same thing, K prime EQ is 1 over K EQ. So if we go to the next example on the next slide, I'll give you a second to write that down. If we go to this example, it says, based on the previous example, predict the equilibrium constant for the formation of NOCl, so the reverse reaction. So in this case, when we go through, you can set up an ice chart again and use the data, get more data and do all that, but it's a lot faster if you use this K prime rule. So K prime is 1 over K, so I take 1 divided by my answer from the last slide, and I get 12.5. Awesome, done. All right, heterogeneous equilibria. Homogeneous equilibria is when all the reactants and products are in the same phase. So they're all aqueous, or they're all gases, or they're all in the same phase. In a heterogeneous equilibrium, there's more than one phase in the reaction mixture. So we have to take that into account when we do these equilibrium expressions. Remember what I said, solids, liquids, and solvents are usually in the form of a liquid, do not appear in the equilibrium expressions. So an example here, write the equilibrium law for the dissociation of sodium hydroxide as a solid in water. So if I were to do that, oh shoot, sorry, I thought it was there. Your KEQ value, again, always products divided by reactants. It's going to be your concentration of Na plus times your concentration of OH minus divided by nothing, because you're not allowed to put your NaOH in there. So that's it. Multiply those two numbers together, and you've got your KEQ expression. So these end up getting much simpler because you don't have to actually do a division. All right, so now that we've gone through some examples of calculating K, I just want to take a minute to talk about what that means. The magnitude of K. Basically, it tells us which way the equilibrium lies. So are we making lots of reactants, or are we making lots of products? So let's read through the points. When KEQ is very large, so K is much, much bigger than 1, the equilibrium lies very much to the right, which means your products are favored. If KEQ is very small, much less than 1, the equilibrium lies very much to the left, which means reactants are favored. When KEQ is neither very large nor very small, so when it's around 1, neither reactants nor products are favored at equilibrium. Okay, so that means you're kind of making almost equal amounts of reactants and products. So there's sort of a quick diagram. I think I got that out of your textbook. When KEQ is very small, the reaction hardly proceeds at all because the reactants are favored. When KEQ is very large, the reaction proceeds nearly to completion and you have almost all products and no reactants left. And then in the middle, you've got about the same or similar concentrations of reactants and products. So if we go back to here, my concentration, or my value, sorry, for KEQ for this first part of the question was 0.08. So that's less than 1. Not a lot less than 1, but a little bit less than 1. So basically that says that reactants or products are favored. In this case, because it's much less than 1, hold on, let's jump ahead again. Because it's much less than 1, reactants are favored. Now, if we look at our ACE chart, I'm going to toggle back and forth for a minute. If we look back and forth, when I said the KEQ was 0.08, it's not very small. It is less than 1, and your reactants are favored, but it doesn't mean that no products are formed, because we did have some products formed. We had a little bit of a concentration, but we had more reactants at equilibrium because your KEQ was small. If we were to reverse it and get a larger value for KEQ, then products are favored. So you can see in both cases, here my products are favored, which is my NOCl. Here my reactants were favored, which again is my NOCl. So basically it means it doesn't matter if I start with only reactants or only products or a mixture of both. This reaction, when I start off with that concentration of NOCl at a certain temperature, I'm going to end up with more NOCl than NO and Cl2. So that's basically what it means. I'm going to stop there for today. We're going to do more of these examples in class.